Welcome to the part 2 of my video lectures regarding the formula derivation of external inductance of a conductor. In part 1 of my video lectures, I discussed about the formula derivation of internal inductance, and now we will determine the formula of external inductance. Once we determine the formula of external inductance, we will ready to determine the total inductance of conductor number 1 by adding the internal and external inductance of conductor number 1. The objectives of this lecture are: learn the philosophies in deriving the external inductance, learn the physics of derivation, and learn the mathematical method like differential and integral calculus. This is the formula of internal inductance that was already derived in part 1 of my lectures. So once we derive the formula of external inductance, which is the topic of this lecture, we will determine the formula of total inductance of conductor number 1, which is L1 is equal to 2 times 10 to the negative 7 logarithm D over R1 prime in Henry per meter. This slide was already discussed in part 1 of my video, and I think it is also necessary to discuss this for the benefit of viewers who did not see the part 1, and also for the review of those viewers who already see the part 1 of my video lectures. As shown in the figure is the conductor with current flowing in it. This conductor will generate a magnetic fields or magnetic flux inside and outside of the conductor. And the directions of this field will be known by using right-hand rule. The thumb points will flow in the directions of the current, while the fingers will curl in the direction of the magnetic field. In this figure, it shows a conductor 1 meter long and current is flowing in it. We know already that the conductor generates internal and external magnetic fields. But this time, we will focus on external magnetic field, Hx, shown as blue dashed lines. Again, Hx is the external magnetic fields or magnetic flux. R is the radius of conductor. X is the assumed radius of external magnetic fields or magnetic flux. I is the current flowing. Please note that the current to be considered is the whole current I, because it is the current that was enclosed by the external magnetic fields. Using again what was stated in Ampere's law, that a magnetomotive force MMF around any closed path is equal to the net current in amperes enclosed by the path, which is also equal to the surface integral of the magnetic fields or magnetic flux intensity at Hx around the circular path. So the equation is the same with what we are used in part 1 of my video lectures, but the difference is the notation of current, which denotes the whole current. Mathematically, MMF is equal to the I enclosed, which is also equal to the surface integral of Hx times ds, whereas the distance along the circular path, I, the current enclosed, Hx, external magnetic field or magnetic flux intensity or strength, and x is the radius of the circular magnetic fields. Therefore, I enclosed is equal to the surface integral of Hx times ds, as determined in previous slide, that I enclosed is equal to the surface integral of Hx ds, and s is the distance along the circular path of the external magnetic fields, which is practically a circle, and the integral of ds is simply 2 pi x, which is also the circumference of the circle, while Hx remains constant because it moves at all points along the circular path at distance x from the center of the circle. After integration, the equation will become Hx times 2 pi x is equal to I, and equating Hx is equal to I over 2 pi x in ampere turn per meter. We already derived the formula of Hx in the previous slides. As we will see in this figure, this Hx has circumferential surface 1 meter in length. The next thing we will determine is the density of the magnetic flux, and this is the number of magnetic flux in Weber in a certain area in square meter. We will assume that the thickness of this circumferential surface is dx. The small area dA that we are going to consider is only the small slice of the circumferential surface with thickness ds and 1 meter in length. So the magnetic magnetic density we will be going to determine is dBx in Weber per square meter. Based on the study by physicists and scientists, the number or the amount of magnetic flux to be produced is dependent on the magnetic properties of the material. In our case is conductor. The magnetic properties of the material was called as permeability U of the material or conduct. In that principle, we can say that the magnetic flux density Bx has mathematical relation with magnetic flux intensity Hx and with permeability U of the conduct. Therefore, the number of magnetic flux density Bx will depend on the strength of the magnetic flux intensity Hx and with the properties of the material which we call as the permeability mu of the conduct. Mathematically, the relation will be written as Bx is equal to mu times Hx. The fact that the actual transmission lines are exposed to the environment with the presence of air, and since air is also a matter or a material, it has also permeability like the conduct, and this is called as the permeability of free space mu naught. Since we have two kinds of permeability of conductor mu and permeability of free space mu naught, the ratio of this permeability will be called as relative permeability mu r. Mathematically, mu r is equal to mu over mu naught, where mu r the relative permeability, mu the permeability of conductor, and mu naught the permeability of free space or air. Based also in the study, the relative permeability mu r of non-magnetic material like wood, plastic, glass, copper, and aluminum is equal to 1. Therefore, the permeability of conductor mu will be equal to permeability of free space. Since we already determined the magnetic flux intensity Hx and the permeability of the conductor mu, we can determine the magnetic flux density Bx by substituting the formula of Hx and mu. Therefore, the formula of magnetic flux density Bx is equal to mu naught I over 2 pi x. We already derived the magnetic flux density Bx in terms of magnetic flux intensity Hx and permeability mu. The next thing we will determine is the number of magnetic flux using the formula of magnetic flux density in terms of the number of magnetic flux and area A. What we are going to determine next is the number of magnetic flux. We already have magnetic flux density B, but we need to determine first the area wherein the number of magnetic flux will be computed. In this figure, the red dashed lines is the small slice of the circular magnetic fields, and this is the area to be considered where the number of magnetic flux will be determined. This small slice has thickness dx and 1 meter in length. Since it is a very small area, in calculus, it will be considered as infinitesimal area A, and this will be called as dA. To get dA, it is simply the width dx multiply by length of 1 meter. So dA is equal to dx in meter times 1 meter. Therefore, dA is equal to dx in square meter. We have infinitesimal area dA. It is also in this area that magnetic field density Bx as already determined, and it is also the area where to determine the number of magnetic flux. Since it is a very small area, it is right to say that Bx is dBx and flux x is d flux x. Therefore, the formula will become dBx is equal to d flux x over dA. Equating d flux x is equal to dBx times dA. Substituting the value of dBx in this formula, therefore, d flux x is equal to mu naught I over 2 pi x times dx. You will notice we started from Ampere's law to get Hx, then from Hx we get Bx, then from Bx we get d flux x. What we are going to achieve is the internal inductance of the conductor. And based on electromagnetic principle, the inductance L is equal to the flux linkage divided by the current I, where the flux linkage is the linking of magnetic flux within the circuit. So we need to determine first the flux linkage before we can can determine the inductance L. In this figure, we will notice that the external magnetic flux with the radius of X is enclosing the entire current I or the single turn conductor. Therefore, we can say that the external magnetic flux is linking the single turn of the conductor. Therefore, the flux linkage of the circuit is equal to the number of magnetic flux times one turn. So the flux linkage of the circuit is practically equal to the number of magnetic flux. Since the number of magnetic flux is equal to mu naught I over 2 pi x times dx, therefore the flux linkage x is equal to mu naught I over 2 pi x times dx. What we determine is only the infinitesimal flux linkage of the circuit of the area dA. But what we need to determine is the external flux linkage of the conductor. Please take note that the external magnetic flux has been assumed considering only the first conductor of the single phase system. And the flux linkage we already determined is the one that links only the first conductor. It is right to assume also that the external magnetic flux will link also the second conductor of the single phase system. At this moment, we no longer know the boundary where the external magnetic flux of the first conductor will link the second conductor, which will result to have an induced voltage in the circuit. In our premise to have a boundary for external magnetic flux, we will assume a two circle that enclose the external magnetic flux as shown in this figure. This circle has distance d1 and d2 from the center of the conductor. Since we already determined the flux linkage in the small area, we can determine the external flux linkage by integrating the flux linkage from d1 to d2 or getting the external flux linkage from the surface of the conductor up to the circular surface of point P. We already have the equation for flux linkage of the small slice of circular strip as mu naught I over 2 pi x times dx. Since the permeability of free space is equal to 4 pi times 10 to the negative 7, substituting it to the above equation will become the flux linkage x is equal to 2 times 10 to the negative 7i over x times dx. To get the total external flux linkage of the conductor from d1 to d2, we will use integration, and the equation is flux linkage external is equal to the integral from d1 to d2 of 2 times 10 to the negative 7i over x dx. This equation has constant term which is not subject of integration. So by moving the constant term outside of the integral, the equation will become flux linkage external is equal to 2 times 10 to the negative 7i integral from d1 to d2 of 1 over x dx. The integral of 1 over x is ln x. So the equation will become flux linkage external is equal to 2 times 10 to the negative 7 times I ln x to be evaluated from d1 to d. To get the area under a graph or function ln x, we will use the fundamental theorem of integral calculus, wherein the area under the curve of a function is equal to the difference of the integral of a function and to be evaluated to d1 and d2. By equating d1 and d2 to ln x and using this formula, we get flux linkage external is equal to 2 times 10 to the negative 7i ln d2 minus ln d1. Applying the logarithmic rule, the equation above is also equal to 2 times 10 to the negative 7 times I ln d2 over d1. We already derived the external flux linkage of the conductor, which is flux linkage external is equal to 2 times 10 to the negative 7 I ln d2 over d1. From the formula of inductance, as L is equal to flux linkage over I, we will substitute the equation of external flux linkage. Then the equation will become inductance is equal to 2 times 10 to the negative 7 I ln d2 over D1 over I. Current I will be cancelled and therefore the external inductance is equal to 2 times 10 to the negative 7 ln D2 over D1. Since we have derived the internal and external flux linkage of conductor number 1, the next to derive is the total flux linkage and total inductance of conductor number 1, wherein the flux linkage of conductor number 1 is the addition of internal and external flux linkage that we already derived. So if we want to find the total flux linkage due to current in conductor number 1, then we need to add the internal flux linkage and the external flux linkage as internal flux linkage plus external flux linkage. Therefore, the flux linkage of conductor number 1 is equal to 1/2 times 10 to the negative 7i plus 2 times 10 to the negative 7i ln D2 over D1. This is the end of my lectures about the derivation of external flux linkage and external inductance of conductor number 1. Thank you and hope you will continue to watch my next video in part 3.